So I'm going to give you a couple of announcements. One is that I'll be posting the lab for yesterday, today. It's naming compounds. It's a dry lab. You don't need to worry about any safety issues or anything like that. Just don't poke yourself in the eye with a pencil. You do want to write it up in your lab notebook. So there's going to be a background. There's going to be a safety. There's going to be a procedure. The procedure is probably going to be the directions for how to name compounds and how to get the formula of compounds. And then for the calculations, you don't really have calculations, but maybe you have examples of how to do it. I'm also supplying you some practice sheets with lots of practice for doing this. And then also there will be an assignment. The assignment is different than the lab notebook. Sometimes you want to put the assignment in the lab notebook, but you don't want to put the lab notebook in the assignment. So there is some overlap there. How do you know that it's the lab assignment? It'll say lab assignment. How do you know it's the lab notebook? Well, you're supposed to follow those general directions for a lab notebook. Introduction, safety, procedure, data, calculations, results, and discussion. Okay. So that being said, I will also be posting hopefully your homework assignment for Module 2. Or is it Module 3 by then? Module 3 today. And also I'll be posting a couple of lectures to finish out the last bit that will be on your exam. Your exam will be next week, Friday. You'll also have a quiz on Module 3 on, I think, Wednesday. So Wednesday, quiz, Friday, exam. We'll also be starting Module 4 next week because it is, well, week 4. The modules roughly line up with the weeks. You don't have any requirements for Module 4 while you're finishing up Module 3 and taking the exam, but it's going to be there for you to look at. All right, that being said, does anyone have any questions?
Oh, yes, I do have a question. This is Jessica. Where will the lectures be posted?
I'm going to post the lectures in the modules.
Okay.
So Module 2 lectures will be posted, let's see, Module 3 lectures are going to be posted in Module 3. I think there's already one posted.
The one from Friday?
Yeah.
Okay. For some reason, I didn't see it, but I'll check again.
Let me check real quick here. Let's see. I'm going to go to boom, files. I'm going to Module 3. Yep, there's one video.
Okay.
In Module 3. It's called Atoms, Molecules, and Ions videos.
Oh, in Module 3. Okay. And
yeah.
Is that the one from Friday or?
Yeah, it's actually, okay. I think it was from Friday, but it came, well, actually Friday was just a Q&A.
Oh, okay, perfect.
And that may have been from Wednesday, actually, or maybe one that I just recorded and posted. But I'm going to start recording and posting videos instead of having you guys just sit around and listen to me talk about lectures. This is going to be a time for us to do problems, because if you can't do problems, you can't pass the exams. If you can't pass the exams, you can't pass this class. So I can be very helpful in helping you attack problems, approach them, how to think about them, how to write out solutions. And what's going to be very useful for you is that I'm going to show you the kind of work I expect to see on the exam if you want full credit. This is not one of those classes, and there aren't very many like this, where they say, you know what, if you just do something that's good enough, I'll give you full credit. I know you don't run into those classes at CR, not very often. And this isn't one of those. So good enough is not an A. Excellent is an A. Good enough is a C. All right. That being said, questions from the book or the homework or the labs. I mean, you can ask a question about the, hey, what's this with the cord of wood baloney, Tony? You know what I mean? All right. So go ahead. Who wants to ask? To ask, you unmute yourself and vocalize your question.
This is Harry. I have a question in regard with number 6 on the lab assignment.
Which one?
The density lab for
Okay,
question
so
6.
I'm gonna pull that up right now, and I'm gonna
Can-
share my screen so that we can all see number 6 together. This always takes a little bit of time. And now you should all be able to see what's on my desktop. So I've got this oxoanion search you can see there. Density lab, and I've got my Zoom session here. So can everyone read number 6 here? You should notice the density of the floating wood is pretty close to the density of water.
yeah.
The density of submerged wood is significantly less dense than the density of water, and the density of pennies and dimes are more dense than water. So what hypothesis might you have about the density of an object compared to the density of water, about whether it sinks or floats? Well, what do we know about the piece of wood that's floating in the water? Its density is close to that of water, right? And when you sink it, its density is less than water. So that's kind of an interesting thing. The reason it is the same density as water when it floats is because it's not displacing its full volume. And so what's happening there is that, I hope they're not coming for me, because if they're coming for me, I'm in trouble. All right, so if the reason the density when it's floating is very close to that of water is because anything that floats in water, neutral buoyancy is about the same density of water. You guys happen to be pretty close to the density of water. I'm one of those people that I jump into the water and I sink if I blow out my breath, and I float if I hold my breath. So it's kind of difficult once I blow out my breath and sink. I can't really grab more breath and float, so I have to paddle up to the top. Actually, I haven't been in the water for a long time, and I've gotten fatter, so maybe I'm not that way anymore. I might just float all the time. At any rate, people are pretty close to the density of water. Now, the piece of wood having a density of 1, when you don't push it down, it's because it has a smaller volume than you should have by submerging it completely. When you submerge it completely, the density goes down because the denominator goes up, the volume goes up. All right, so the density of wood, and here I'm going to share with you. And Harry, help me out here. What did you get for the density of your wood when you submerged it?
Oh shoot! I don't have my journal on me at the moment. I left it.
Do you have a general idea?
No.
No.
No, sorry.
I'm guessing it was probably around 0.7 or something like that.
Yeah, I think so.
And the density of the penny, I don't know. Density of the dimes, I don't know. But nonetheless, the density of the pennies is close to 2 or 3. Density of dimes are close to 2 or 3 grams per centimeter cubed. Or I should say grams per milliliter. A gram per milliliter and a gram per centimeter cubed are the same thing. So I'm going to go to a new share here. And here's my new share. So I've got the density of this. Now this floats, this sinks, and when the density of the wood was equal to 1 gram per milliliter, it basically floated on top, right? So here it looks like if it's less dense than 1, it floats, and if it's more dense than 1, it sinks. That would be your hypothesis, right? Okay.
Right. Okay. All right. Thank you.
So we're not looking for groundbreaking, you are going to make it onto a Science magazine type of hypothesis here. We're just looking for the simple stuff right now, if that makes any sense. Okay, good question. Who's next? Okay, since there is no next, then we're just going to do some problems from the back of the book rather than do problems from what do you call it, the homework sets. I'll leave that to you to figure out if you have any questions. So I'm going back to chapter 1, and I'm going to take a smattering of problems. I'm going to write the problem out on a piece of paper. I will show you how I tackle it, and then we're going to go on from there. Okay, so here's a problem. It says you have a solution of sodium chloride dissolved in water. So the question is, how would you separate them? Okay, so let's think about some of the different properties of sodium chloride. Sodium chloride, solid at room temp. Water soluble, definitely. Water, liquid at room temp. I think that we all know a little bit more about water than we know about sodium chloride. And we can also say for sodium chloride, it looks like a white solid. It's crystalline. Water, liquid at room temp. Boiling point is 100 degrees Celsius. Freezing point is 0 degrees Celsius. You should memorize those things. They're not too hard to remember, 100 and 0. They're very convenient. So these are some good properties. So based just on this set of properties, you might be able to figure out a way to separate them. And I think this way to separate them is to boil. Okay. Oh, we have someone else in the waiting room. So I'm going to boil the solution, condense the steam into water, and then once all of the liquid has boiled off, the remaining solid will be sodium chloride. So there you go. That's simple. In fact, back in the olden days when the people who lived by the sea, and I'm talking 2,000 years ago, salt was a very rare commodity. You've probably heard of the what do you call that? There's some sort of pathway or trail in Europe where people would carry spices and stuff up and down the trail and do trade. Salt was a big deal. Salt was worth its weight in gold. So when you live in the inlands, it's hard to get salt. So where do you get it from? You get it from someone who's trading it from the coast. How do you get it from the coast? And the answer is simple. Just take some seawater, put it in a container, and let the water evaporate. What's left behind is this crusty stuff that's salt. Okay, all right. So there's that question. Now I'm going to ask you a question. How would you separate sand, salt, and iron filings? I'm going to give you about 1 minute to think about how you would separate these as efficiently as possible. And let's imagine that you have common tools that are around, like, you know, containers, water, heat. You can run to Harbor Freight and pick up tools if you need them. So try and think of a way to separate these things. Okay, regardless of whether or not you came up with a solution, you can see how I'm starting my solution. I'm writing down some properties of each. So these are all solids at room temp. Salt is soluble in water, but these others aren't. So that might be very useful. And we already know that if we dissolve or add water to the mixture and dissolve the salt, we can separate the water from the salt easily by heating it. What about magnetism? Not attracted to a magnet. And this is not attracted to a magnet, and this is attracted to a magnet. As far as melting point goes, this melts high temp. This melts at a higher temp. And this melts at probably the lowest temp of all, although it could be tied. So trying to separate these by melting them, who knows? And again, these are not things that you have rolling around in your head. I certainly don't have them rolling around in my head. So I'm thinking about all of this, and I'm thinking, well, shoot, the easiest thing to do would be to add water to make it slushy, stir with a magnet. Now, what's going to stick to the magnet? The iron. Okay, so you stir it with the magnet and you get all the iron. And when you pull it out, how do you make sure you're not taking any salt water with you? Rinse the magnet and iron off back into the container. Stir with the magnet, remove the iron and rinse. And then you dry the iron and you get rid of the water. So we've separated the iron from all of this mess. How do we separate the sand from the salt? Well, remember, the sand has not dissolved, but the salt has. So then we're going to pour it through a filter. And we're going to use whatever filter we need to separate the sand from the liquid. So that means you're not going to use a very, very fine filter if you don't need it. If you can get away with like a sieve of some sort, that's what you're going to do. You're going to rinse the sand off with water to remove all of the salt water from the sand. Put the sand off to the side. And you're going to dry it, and you've got the sand. And now you have salt and water, and you're going to heat to remove the water. And boom, you separated those three things. And the last thing I'm going to ask you to think about, and you don't need to answer this, is what have I done here in the separation? Was that a physical separation or a chemical separation? I'm going to let you think about that for a second. Okay, now why do you think it is what you called it? Okay, that being done, the answer is it's a physical separation because the properties of each of these items has remained the same afterwards. It's still sand, it's still salt, and it's still iron. Okay, let's take a look at another question here. I'm going to skip to the review part. And we'll look at some problems in the back here. A typical laboratory, I'll try to write this a little more neatly. Am I recording this? I think so. Okay. A typical laboratory beaker has a volume of 250 milliliters. What is its volume in cubic centimeters? And in liters, in cubic meters, and then in cubic decimeters. Well, there, now you can see it. My handwriting looks crappy, but that's all right. All right, so we want to take the 250 milliliters and convert that into cubic centimeters. Now, how do we write the symbol for cubic centimeters? Cubic means to the third power. So there's that. We want to take the 250 milliliters and turn that into liters. we want to take the 250 milliliters and turn that into cubic meters. Whoops. And we want to take the 250 milliliters and turn it into cubic decimeters. Okay, the answers to each of these are 250 centimeters cubed, 0.25 liters. Let's see, 0.25 decimeter cubed. And this one I can't really do in my head, but I know it's a really small number, like a 0.000025, something like that. Okay, and this is a wild guess. Now let's say that each of these happen to be right. And this is the kind of work you showed on an exam for this problem. And the problem's worth 10 points, you get 1. That's it, because you didn't show any work. So let me show you how to show the work. So for this first one, you have to know that 1 milliliter is equal to 1 centimeter cubed, and this is exact, which means we have infinity significant figures for both ones. So to show the work, you would write 250 milliliters times 1 milliliter on the bottom, 1 centimeter cubed on the top, and these milliliters would cancel. And this is a part where if you show them canceling, that's okay. If you don't show them canceling, that's also okay. But they must be in the correct orientation. That is, one in the denominator and one in the numerator, denominator, numerator. And so we get 250 centimeters cubed. And this original number here has 2 significant figures, as does this one in our conversion. Okay, so this would be how we do the first one. Now, how do we do the 250 milliliters to liters? There are 2 ways to do it that are both correct. One way is to take 250 milliliters and say that that's equal to 250 times 10 to the minus 3 liters. This method here is called substitution. Now, I know we think of substitutes as being not as good as the original, like the sugar substitute is not as good as the original, okay? But that's simply not true. In this case, the m is the substitute, the 10 to the minus 3 is the real thing. So I've substituted the real thing for that milli. So I could clean this up and make it 0.25 liters. Now you might be wondering what happened to that last 0 there? Well, that 0 is not significant. And if I write it in here after the 5, then it is significant. Trailing zeros with a decimal are significant. So I want to leave that off. So this is 0.25 liters. That's one way to do this. Another way to do it is to do this. And this is more in line with what we had done above. There's 1,000 milliliters per 1 liter. And that's a value you should memorize. Okay, you should just outright memorize that. So when we clean this up, we get 0.25 liters. Great. Now, what about this one? 250 milliliters to meters cubed. Well, I know I can go from 250 milliliters to a centimeter cubed, and then I think I can go from a centimeter cubed to a meter cubed because I know something about centimeters and meters. So here's what I know. I know that 1 milliliter is 1 centimeter cubed, and I know that 100 centimeters is 1 meter. This is probably one of the first things you learned about the metric system back in grade school when your teacher pulled out a meter stick and he said, "Hey, what is this?" And you all say, "A yardstick." He goes, "Nope, it's a meter stick." And he pulled one over your eyes. And then he went on to explain that it's divided into 100 units. Each of those is a centimeter. Okay, so you probably know this and you now have memorized this. So how do we use this to convert? Well, here's a mistake. What I'm about to show you is wrong. You might be thinking, why is he showing me something that's wrong? And the answer is so that you don't make the mistake in the future, okay? You learn more from your mistakes than your successes. So this is wrong. So you might be asking, how in the world is that wrong? I cubed both sides, right? Well, let me show you how it is wrong. So this is 1 meter, this is 1 meter, and this is 1 meter. So we're going to call this the length, the width, and the height. So when we take the volume, which is the length times the width times the height, we get 1 meter times 1 meter times 1 meter, which is 1 meter cubed. Now, this is also 100 centimeters. This is 100 centimeters, and this is 100 centimeters. So it's also equal to 100 centimeters times 100 centimeters times 100 centimeters, which is 1 million centimeters cubed, not 100 centimeters cubed. So what was wrong with what I had done here when we know for a fact that that is true? Well, the problem is when I did this, I cubed the meter. I cubed the 1. I cubed the centimeter. I did not cube the 100. This would have been okay. Put a parentheses around the whole side and cube the whole side. That'd be okay. So let's go back to the problem. We want to convert 250 milliliters to meters cubed. And the way we're going to do that is convert that to centimeters cubed, then to meters cubed. Here's how I would do it. Now this way I can see very easily that I have 3 centimeters on the bottom, 3 on the top, and therefore they cancel. I'm going to be left with 3 meters in the top here, so that's going to be meters cubed. And here we're going to have basically 250 divided by a million, which puts us at 0.00025 meters cubed. So when I divide this by a million, that's 10 to the 6. So it becomes 250 times 10 to the minus 6, which means I move the decimal over. Since this is a minus 6, I want to make this number smaller. So 1, 2, 3, 4, 5, 6 times. So that's how I get the 0.00025 meters cubed. And so that means my estimate was wrong by 1 number, or tenfold, I should say. So this is one way to show the answer, and that's perfectly acceptable. Here's another way to show the answer. That would be okay. This would also be acceptable. See, when we, sorry, that should be a times. When we put the ratio down, we can cube both the top and the bottom simultaneously with that big parentheses. So which one is my favorite way of doing it? And the answer is this way. Because I don't need to mess around with this and figure out that it's 10 to the 6. I can just remember this conversion, which is very easy to remember. I got it solid, so I go from there. Any questions about that? Any questions? All right, so now I'm expecting a little bit of a contribution from you guys. Are you okay with what we've done so far? If so, give me a thumbs up. I'm waking you guys up, huh? Go to your participant list, open it up. At the bottom, go to the more and pick your thumbs up. All right, let's move on then. I'm going to clear the thumbs. Okay, let's take a look at another problem then. Oh, we did not finish this problem, did we? There is one more thing. We need to take the 250 milliliters and convert it into decimeters cubed. So what would be the tack that I would take here? Well, I'd take the milliliters, turn it into centimeters cubed, then the centimeters cubed, turn it into meters cubed, then the meters cubed into decimeters cubed, because I happen to know that there are 10 decimeters in 1 meter, because that same teacher who brought out that meter stick and said, this is 1 meter divided into 100 centimeters. It's also divided into 10 equal parts, and each one of those is called a decimeter. So this one, I'm going to leave for you to do. It's good practice. The other times that you do stuff like this is when you have to convert things by area. Okay, let's take a look at another problem, okay? So again, this is from the back of the book. I'm going to look at problem number Problem number 15 here. It says, you can identify a metal by carefully determining its density. So kind of a little aside here. If you've done the density lab, give me a thumbs up. No thumbs up? 1 thumbs up. Okay, cool. When you do the density lab, you might find something interesting there. You might have already known it, but maybe you didn't, but it is pretty interesting. Okay, you can identify a metal by determining its density, which is what you kind of do in the density lab. And here we have a piece of metal is 2.35 centimeters by 1.34 centimeters by 1.05 millimeters, and is 2.361 grams. Which metal? So nickel is 8.91 grams per centimeter cubed. Titanium is 4.50 grams per centimeter cubed. Zinc is 7.414 grams per centimeter cubed. And tin, SN, is 7.23 grams per centimeter cubed. Okay, so based on this information, we're supposed to be able to figure out which metal it is. Okay, so we should know that density is equal to mass divided by volume. We also know that all of these values are in grams per centimeter cubed. So we would like to calculate our density in grams per centimeter cubed. Now there's one little oops we have here, and that's this 1.05 millimeters. So I'm going to take that 1.05 millimeters and I'm going to convert it to centimeters. Now, that same teacher who showed you that yardstick probably showed you a little centimeter and said, see this little centimeter? It too is divided into 10 equal portions. Each one of those portions is a millimeter. So this is something you probably know very well. 10 millimeters is exactly 1 centimeter. So we can take this 1.05 millimeters times 1 centimeter over 10 millimeters, and we can get 0.105 centimeters. Okay? If you know these numbers really, really well and you just want to move the decimal over one place, You'll get partial credit. You won't get full credit for doing the answer right. You'll get partial credit. I want to see this type of work because even for this easy stuff, you should especially be able to show your work. So if you knew this was the answer beforehand and you can't show how to get there, then that's no good. Okay, so you need to show your work. So now we can get that the mass is 2.361 grams and the volume is 2.35 centimeters times 1.34 centimeters times 0.105 centimeters. So I'm going to get centimeters cubed here. And here you can see that each of these beginning numbers has 3 significant figures. So I'm going to get 3 significant figures here. Okay, and I'm going to kind of ish it to get what I think the answer will be kind of close to. So 2.35 times 1.34 is probably something like 2.5 times 1. So this is around 5. And 5 times 0.1 makes that around 0.5. Okay, so I'm going to have 2.361 divided by 0.5. And that'll go into that about what? 9 times? No. 1, 2, 3, 4, 5 times. So 5-ish is going to be my final answer at the end. So I'm betting it's titanium. But at any rate, let's go ahead and figure out the answer. I need my calculator. What did I do with it? Okay, here we go. Clear. 2.35 times 1.34 times 0.105. Then we get 0.33. And I had 5, so I'm off. I might not be close on 10. So we get the volume is 0.330645. And I'm putting my little arrow pointing at the 0 because that's where I would round to if I were done, but I'm not done. So the density is 2.361 grams over 0.330645 centimeters cubed. So I'm going to put divided by 2.361. And I know that's not the answer because I really did the inverse. So I'm going to hit inverse. And I get 7.14 grams per centimeter cubed. So it looks like we actually have zinc. Okay, so that's how you do a problem like that. Now, why do I only have 3 significant figures here when I have 4 here and what looks like 6 here? And the answer here is I have 6 figures written down, but only 3 are significant. And since this is my final answer, now's the time to round. So I round it to 3 significant figures, which is where this would have rounded also. Okay, are we good on that? Thumbs up. We're just going to make this a regular thing. When I'm done with the problem, if you're okay with it, give me a thumbs up. If you don't give me a thumbs up, I'm going to call you out and ask, what can I help you with about the problem? Or what is it about the problem that I'm missing? Ashley, what am I missing here on this problem for you? Or you can give me a thumbs up, one of the two. Ashley, are you there?
Yeah, sorry. I just think that it's going to take practice, just going through and working
Okay.
them. And
You don't have any questions though?
no, I was just thumbs upping that, I'm
Okay.
grateful that we're going over it.
You know where the thumbs up is?
Yeah.
All right. Give me the go more and thumbs up. That way you don't have to pull out your mic and talk. Excellent.
This is Jessica.
That's an emoji thumbs up, Ashley. Do you know where open up your participant list, Ashley. Do you see at the bottom of the participant list, it says more? Excellent. So that's the thumbs up I'm looking for, Ashley. So I would give you my thumbs up, except, there's my thumbs up, Ashley, for your thumbs up. All right, Jessica, I interrupted you. Go ahead.
Nope, you got it. I was just going to ask you to move the paper because there was some things on the side that weren't in view, but it looks like they're in view now. So
Okay.
for the
Excellent.
video.
So let's go on and do some more problems. Okay, you are on a diet. Diet of 1,200 calories per day. How many joules? So that's the question. 1,200 calories a day. So that means like one Big Mac a day, one Whopper, one huge chocolate shake. This is a starvation diet. So if you're on that diet, I guarantee you're going to lose weight. All right. So we're going to take our food calorie and turn it into chemical calories and turn that into joules. So you see me doing this quite a bit where I kind of map it out what I'm going to be doing. And for these maps, I also like to get the conversions for each one of these transitions here. So one big calorie or food calorie is 1,000 chemical calories. So uppercase is the symbol for a food calorie, lowercase is for a chemical calorie. And one chemical calorie is 4.184 joules. And for each of these that I need a conversion factor, I personally like to write out equivalences and not ratios. So I'm going to start off with 1,200 calories. And when I look at these two conversions, I know that I want to cancel my large cal, and this conversion has a large cal, so I'm going to take that large cal and put it on the bottom, and I'm going to take the other side and put it on the top. And I'm doing that simply because I want the cals to cancel. And the uppercase cal cancels with the uppercase cal, not the lowercase. Next, for number 2, I'm going to use this conversion, and I want to cancel the lowercase cal, so I'm going to put this guy on the bottom. And I'm going to put this guy on the top. And my lowercase cals cancel. So you can see that roughly I'm going to have this times this, which is 1.2 million, times 4.184. So 1.2 times 4 is what? 6? No, not quite that much, maybe 5. So I'm going to have like 5 million as my answer. Now this is exact. So I have infinite zig figs here. This is infinite zig figs, and this is 4 zig figs. Turns out that the conversion between joules and calories is not defined. So 4.184 is 4 zig figs. And here, it's 1,200 calorie diet. This is 2 zig figs, which is great because that meant if you ate 1,249 calories, that would technically round down to 1,200, and you'd still be on your diet. I'm just saying. All right, got to look at all the angles here. So let's do the calculation here. So 1,200 times 1,000 times 4.184 is equal to, and here I don't like the way that's written, so I'm going to have it written in scientific notation. Well, there's so much light going on here that it's glaring. Let me see if I can turn the light off here. Well, that wasn't any better. So here, to turn this into something different, I have this thing here that says science engineering here. So second, boom, toggle over to science and hit equal. And now it's in scientific notation. So I get 5.0208 times 10 to the 6. I need to include my unit. You always see me carrying my units through the calculations. You'd better do the same on an exam. 2 zig figs. So what do I round this to get 2 zig figs? I don't care what the 10 to the 6th is. That does not affect the number of significant figures. I look right there. So this is something I didn't talk about in rounding, but I'm going to say it outright right here. When you're rounding, you keep the numbers to the left first. So I get to keep 2 digits. So I'm going to keep this number, the 5. I'm going to keep this number, the 0, but I'm going to look to the right. And since that's a 2, it rounds down. So I don't think we would argue that 5.0208 rounds down to 5.0. So that would be the answer. All right, we good? That thumbs up time. All right, here's another one that says, express the following in scientific notation. Okay, so here's how we put things into scientific notation. So first thing I'm going to say is this is going to have a negative exponent. How do I know it's going to have a negative exponent? And the answer is that's smaller than 1. Next thing I'm going to do is I'm going to move the decimal over and count how many times I move the decimal over so that when the decimal is in its new spot, that number will be between 1 and 10. So I'm moving this over 2 times, so I get 5.4 times 10 to the 2, and it's negative. So that's it. So this is going to be a question for you. Will this exponent be negative? If you think it is, put yes. Will this exponent be negative? If you think the answer is no, write no. The question again is, will this exponent be negative? Good. So it's going to be a positive exponent. And we know it's positive because that number is bigger than 1. So let's move the decimal over. So that's where the decimal is implied to be. 1, 2, 3. So 5.462, we moved it over 3 times. I'm going to go ahead and put the plus right there. So times 10 to the plus 3 and grams. Some of you did not notice it, and neither did I, but I made a mistake on A, and it would not get full credit. Here's the mistake. I left the G off. Okay, can't get full credit there. Okay, so there we go. Now let's take a look at the next one. So if you think this is going to be a positive exponent, pick go faster, because that kind of means bigger, right? If you think it's going to be a negative exponent, pick go slower. Negative is go slower. Positive is go faster. Exponent. So remember, bigger than 1, positive, smaller than 1, negative. So is that original number bigger than 1 or smaller than 1? It's a lot smaller than 1. So this is going to be a negative. So rather than rewrite this again, I'm going to move the decimal over 1, 2, 3, 4 times, right? So that's going to be a negative 4. And we get 7.92 times 10 to the minus 4 grams. Okay, and lastly, this one, we're going to move the decimal over 3 times. It's going to be a positive 3 because the original number is greater than 1. So we get 1.6 times 10 to the 3rd milliliters. Now, why did I drop those 2 zeros on the end? And the answer is, according to our significant figures rules, all trailing zeros don't count unless you see a decimal. These don't count. So that's why I don't have them written here. Okay, let's move on. Here's a nice little graphing exercise. And, just in case for the exam, I have you draw a graph and you need to take a picture of it and upload it as a file. You might want to have graph paper sitting around. Okay, so this says plot the data. Kernels on the x-axis. Oh, that reminds me, kernel. I was driving down Broadway and I saw this building being built with red and white stripes. Guess what's going in on Broadway? KFC. See, Colonel, KFC. All right. What would be better than the KFC? You young people don't like fast food, do you? Because you're healthy. We old people do like fast food. What would be better than the KFC? In my opinion, Popeyes. Why can't we have a Popeyes? Okay, no one's got the answer to that? All right. Well, if you want to get rich in Humboldt County, let me tell you, you get yourself a Popeyes franchise and you won't care about chemistry in the future. Heck, I might even come work for you because I like their chicken. All right, plot the data, kernels on the x-axis, mass on the y. Draw the best straight line get the equation. What is the slope? And what's the slope mean? And then how many kernels are there in a handful of popcorn? In 20.88 grams of popcorn. All right, so I got my handy dandy ruler here with my handy dandy purple pen ink on it. So I don't have any graph paper in front of me, so I'm just going to draw a graph real quick. Now, this is the amount of paper I have to work with, so I'm trying to use as much of the paper as I can. Normally, you would want a fresh piece of paper to do this on and make the graph just as large as you can, okay? So it says to put the kernels on the x-axis. So this is kernels here. And it says to put the mass on the y-axis. Now for the kernels, technically what is the unit? The unit would be amount. 1 kernel, 2 kernels, 3 kernels. The mass, the unit is grams. So this is going to be my graph of kernels versus mass. So these are all things that you want in your graph. You want the title, you want the axes, you want the axes labeled, and you want the axes with their tick marks on it. So here I'm going to put little tick marks here. So I have 11 tick marks here. And when I take a look at my mass, you can see that my largest mass is 5.8. So that means that I can do this for each tick mark. I can make each tick mark actually half. So I can make this 1, 2, 3, 4, 5. And if I make my graph just a little taller, I want to make sure I use the full scale of the graph if I can. Okay, so here for the bottom part, let me put my tick marks in. Now, when we look at the, oh wait, the mass kernels on the x-axis, mass on the y. So I did that right. Notice for these tick marks, did I put a number next to each tick mark? And the answer is no. That would have been way too crowded. So I put them on every other. So you don't need to put a number for every tick mark. The idea is we put them evenly spaced so that we can figure out what the tick marks are in between. Okay, number of kernels, I go up to 35, and I have how many tick marks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I make each tick mark worth 3, that would make this 36. So I think that's what I'll do. So this is 9, this is 18, this is 27, and this is 36. And I have not used a portion of my x-axis, but that's okay. I've used pretty much most of it. Okay, so now we plot these data points. We've got 5 kernels. So if this is 9, this is 6, and 5 is somewhere right in here. And for 5 kernels, I've got a mass of 0.836, so roughly there. Okay, this would be a lot easier if I had real graph paper, so I am kind of fudging it a little bit. All right. 12 and 2.162, so the number of kernels is 12, so that's this guy right here. And 2.612 is going to be around in here somewhere. And then lastly, I have 35, which is going to be around in here. And I have 5.81, which is going to put it right about there. Okay, so I want to draw my best line. And here, I'm going to go ahead and extrapolate. Now, when this extrapolates back, it should extrapolate back close to 0, 0, because the idea there is 0 kernel should have 0 grams. It didn't hit it precisely at 0, 0, and that's okay. Okay, because we don't really have that as a data point, although we could consider that. Now, I drew my line to try and get them as close to these dots as is possible. If you have dots like this, not exactly in a straight line, this is wrong. This is not a line of best fit. It's 2 lines. A line of best fit is one straight line as close to all of the dots as is possible without bending the line at all. Okay. So here's the equation of my line. And here what we need to do is we need to figure out what the equation of the line is. So for the equation of the line, we're going to do for the slope, change in y over change in x. Now, according to this plot, can I use these 2 points as my 2 points to get the slope? And the answer is absolutely not. And the reason is that point is not on the line. That one looks like it is on the line, but that one's not on the line. So I can't use it to get the slope. It has to be a point on the line. And this is where having graph paper is really nice, because you'd be able to do something like this. And you'd have a point. So that point there looks to me to be like 18 kernels and 3 grams. So I can use that point to get the slope of my line. Plus I can use that one because it is on the line. Remember, this point here was 5 and 0.836. Okay, so that's important. The points must be on the line to get the slope. So here, my change in y over change in x, I'm going to have 3 minus 0.836, and that's going to be grams. And here I'm going to have 18 minus 5, and I'm going to put kernels here. Okay, and the reason I put grams here is because the y-axis is grams, and I put kernels here because the amount is kernels. So here, when I do the work, 3 minus 0.836 divided by, and that's 13. So I get 0.166 grams per kernel. All right, now how do we get the B value? The B value should be very close to 0, and the answer is simple. We do y equals mx plus b, so y is equal to 0.166, we can leave the units off for now, times x plus b, and let's plug in this 3 and this 18. So here, my y is 3, 0.166 times 18 plus b, and we find out that b is equal to 3 minus 0.166 times 18. Well, goof that one up. 3 minus 0.166 times 18. And I get 0.12. Now, for a math class, you might have been instructed to do this. Let's see, clear 0.166 times 18.
Tony, could you slide your paper down just a hair? The first line is partly cut off.
Yeah,
Thank
there you
you.
go. I feel like my Zoom is over zoomed, or my enlarged. Okay, so here, what you're seeing here is the development of this equation step by step by step. So here's the original equation where I'm trying to figure out B. I plug in a Y, I plug in an X. Here, I multiply these two numbers to get that. Here, I subtract 2.988 from each side. And if I did that right, oh yeah, I wrote down my B incorrectly. I didn't see that decimal there. So there's my B, okay? Now, this type of work, I do not expect to see. This is not a math class, okay? So if you start here and then you plug these numbers in and you jump straight to here, I'm fine. Okay, so now we get the formula looks like y is equal to 0.166x plus 0.012. Now, what could be better than this? And the answer is this. Remember the y-axis is mass, so I'm going to put m is 0.166, and I'm going to put k here plus 0.012. What do you think k stands for? Number of kernels. And here's the equation of the line. Remember, x and y are just placeholders for the real things. And here, these are better placeholders for the mass and for the kernels. All right, now they ask us, what does the slope mean? The slope means 0.166 grams per 1 kernel. And we know that because this is change in y over change in x, and y is the mass, and x is the kernels. Okay, so that's what the slope means. And then lastly, they ask, how many kernels in 20.88 grams of popcorn? So here we can take this equation, and I'm going to show you how I'm going to manipulate it. So here I took the 0.12 and subtracted it from each side. And here I divided each side by 0.166 K. And so here, if I want to figure out how many kernels for a mass of 20.88 grams, I simply plug in 20.88 grams here. And that'll give me the number of kernels. So 20.88 minus 0.012 divided by, oops, I got to go back, equals Is there a way to ish this? What do you think? Isn't this roughly 21 divided by 0.166? Who in the world can do that? I can't. But what if this were 21 divided by 16.6? That's something I might be able to handle. 16 will go into that like 1.5 times, right? Roughly. And then here, this number is 100 times bigger than that. So maybe I've got around 150 kernels. So let's find out what we get. And we get 125. We're going to round to 126 kernels. So 150 is a little off from 126, but ballpark, it's close. And so I can trust my 126 and know I didn't screw it up, and maybe this should have been 1,257. Now, one of the things that I haven't talked about is how do you know how many significant figures to have in your slope? And the answer is you don't really, so I usually just put 3 there. We don't really have a way to teach you how to get the correct number of zig figs there from getting the equation of the line. So we'll just go with 3 for the slope. All right, folks, we've done enough of these problems. When we come back here on Friday, we'll do some more of these problems, plus we'll do some of the problems in the back of the next chapter, chapter 2. Also, I should be telling you this, I'm going to post another video today for the lab for tomorrow. The lab for tomorrow is going to be a mass spectrometry lab. And it's one where you're supposed to make mistakes because that's the natural thing. If you don't make mistakes and you write down in your lab notebook that you just did this perfectly, then number one, you're not really learning anything. You're just writing down the right answer. You're going to make hypotheses on the mass spec lab that are probably going to be wrong. That's good, because your hypotheses are going to be based on what you know to be right, okay? But sometimes they lead you to incorrect conclusions. So getting your hypotheses partially incorrect is perfectly fine. The expectation is that you will learn from that, and the next time you make a hypothesis, it will be better, and it'll probably still be wrong. But you make these little iterations where your hypothesis grows with the knowledge that you gain until eventually, boom, you think you know a subject pretty well and you move on to something else. So it's going to be a good learning experience. I'm hoping to make a video of it where I tell you something, I show you something, and then I say, okay, so now try it for this. And when I say try it for this, you're supposed to take that video and pause it. And you're supposed to come up with something, okay? And when you push that video and you push play, chances are I'm going to say, well, did you come up with something? Because if you didn't, push pause. and you have to go back and think. Okay. It's a learning process, and you will get a lot more from it if you actually try with the process than if you just push play and watch the whole thing. Okay. That being said, thanks everyone for attending. We'll see you Friday at noon, and look for some videos today. And is it as dark and gloomy looking outside where you are as it is where I am? Looks like Armageddon out there. I mean, I kept waiting. I've been up since dawn, and I kept waiting for dawn to fade into day, and it seems like it never has. I've never seen smoke like this before. I mean, I've been in California for a long time, but I've never seen it like this, except for when I was fighting fire. I'd see something like this, but not so far away. This is just wild stuff. And there's nobody out on the streets. It's like, I get it. If there's that much smoke in the air, you might be damaging your lungs by going out there. Unless you're wearing your mask, it probably helps. So you got two reasons to wear a mask now. One, to help protect other people, and two, to protect you from some of the smoke. All right, that being said, turn your mics on and say goodbye to everybody.
Bye, everyone.
Bye, everybody.
Bye, everyone.
Bye, everyone.
All right,
Woo.
thank you for listening. Bye-bye.
Thank you.
Thank you.
Bring questions on Friday.